Our next presenter is Mr. Abdul Hannan Faruqi. He is from IIT Kanpur, and his topic of presentation is the framework for planning, control, and analysis of a drone swarm in agriculture application. Mr. Abdul, over to you.
Good evening, everyone. I'm Abdul Hannan Faruqi, and my friend Ronald, we are presenting a framework for planning, control, and analysis of a drone swarm agriculture applications. So let's begin with a brief overview of the objectives of this project. This is an example of the type of problem that we'll be tackling with the framework. So we have a certain destination and some sources, and a different number of packages are to be fetched from each of the sources to this destination. For example, if there are different farms, we have to fetch some cultivated crops from these farms and assemble them at the warehouse. We can also do the opposite case where we have to distribute seeds from the warehouse to different farms, and both type of problems can be tackled with this framework. So our objectives are to calculate the optimized path for each of the drone in this drone swarm to reach each of the source. And then we want to perform optimal task assignment so that each drone is assigned a specific task and the overall task gets accomplished in the shortest possible time. We also want to tune the controller parameters by implementing first a drone model that can be simulated, and then we want to tune the controller parameters of the drone to achieve the desired trajectory. And we also want to visualize the performance parameters in real time. This is the workflow that we have taken for verification of a framework. We first generate the paths for the drone from the destination to each of the source using PRM. And then using the calculated paths, we feed them to the assignment algorithm, which assigns the task to each of the drone. And after the assignment task is completed, we visualize the calculated trajectories by performing 3D simulation in Simulink 3D animation software. Now, we'll discuss the implementation.
So implementation, first, what assumptions we have taken? First, there can be n drones. So each drone will have same specification. All drones will be traveling at same height. The drones can be treated as a point object. Why? I'll be explaining in next slide. How? Since there are, because we need to consider if we are treating drone as a point object, we will consider it as a only the position part of it, not the orientation part. Fourthly, the battery life is important and is sufficient for the duration of the task. The fifth is the environment which we have taken is not dynamic since there is no moving obstacle. So since there is no moving obstacle, there is no state in the workspace where which is unknown. Okay, since there is no moving obstacle. And sixth point, the system is observable. So we know the current state of the system. Current state of the drone is known. So we can predict the future states as well. Seventh, the map of the environment is obtainable. We feed the map of the environment. Eighth, which we have discussed the problem, the drone loads in the seeds and pesticides from all the sources, from sources to agricultural warehouse and back to warehouse. So these are the assumptions which we have taken. Next, moving on to plot. This is the plot. The left side is the workspace, the right side is the C-space plot. So how we obtain C-space plot? Each obstacle, green, which you can see in the left space, is inflated by dimension r prime, and the boundary of the workspace is shortened by the same dimension r prime. So in this way, the drone is treated as a point object. So drone can travel anywhere in the free space of C space. Next.
We can also mention the dimension r prime is the radius of the
obstacle.
Drone.
Radius of the drone. So next strategy, the drone will attempt to reduce the control costs. Why? Because the battery life is a very primal importance. 45 to 1 hour is maximum battery life. So we try to minimize the time steps such that we can obtain tuned path. Second, tuning more than 3 or 4 parameters becomes difficult. Specifically in PID controllers, attempts is made to reduce the controller computations. Third, we discretize the drone motions for path identification using probabilistic roadmap, which is inbuilt. We have used the inbuilt MATLAB command PRM. So fourth, in addition, we know and we have used the heuristics of the environment so as to determine the path obtained, path formed or not based on sampling density. This I'll be explaining in next slide. So we have used probabilistic roadmap. So next slide. So in probabilistic roadmap, as you can see in this diagram, it's a random search strategy. Okay, so in which input to it is nodes. We have to specify the sampling points, nodes, node distance, start coordinates, goal coordinates. So in a way, it has two phases. First phase is construction phase, in which all the blue part which you are seeing in the diagram is obtained, all the random paths connecting all in the free space. And I have discussed something about narrow passages. So it depends upon the sampling density. If more is the sampling density, it can form path even through narrow passages. And second phase is a query phase, in which after all the blue part is obtained, we join the start coordinates and goal coordinates over the blue node lengths. Next. In our problem, we have actually used PRM to connect the warehouse from where the drone are there to all the 4 agricultural sites at north, south, east, and west. We have found optimal time step, suboptimal in yellow color, and non-optimal in red color. Next. Next. So this is a summarization of all the drones distance to each of the agricultural site. And there we have also taken case of inter-source distance, backslide, in which the distance in which drones can even pass between source, that is north agriculture site to west agriculture site, if some seeds and pesticides are remaining to be supplied, but it can, in order to go back, it can even pass from north to west side. Next.
So now we'll discuss the assignment algorithm. So the whole problem is represented through this graph, where we have one destination or one site to which packages are fetched from different sources, and the edges connecting them have certain costs associated with them. This cost is the distance of the source from the destination. And the packages are the P1, P2, etc. are the properties of the sources, which is the number of packages they contain. The rules of the assignment algorithm are that each edge traversal incurs a certain cost, which is labeled on the edge, and up to n edges can be traversed at the same time, where n is the number of drones. So each drone moves independently, so we can traverse n edges at the same time. And a single edge can be traversed by 2 different drones with a time gap of at least 2 seconds, so that no collision occurs between them. And we have classified sources into window categories because our destination has some windows through which drones can enter and leave. So some of the sources are maybe proximal to one of the window, and other sources are proximal to the other window. So for sources belonging to the same window category, there must be a time gap of 2 seconds for drones that are assigned to those sources. And each visit to a source reduces its property PI by 4, because the drone we are assuming that a drone can lift at most 4 packages at a time. So every time a drone visits a source, it lifts 4 packages, and the property PI of that source gets reduced by 4. And if PI is less than 4, it becomes 0. And if more than one source has less than 4 packages left, then we consider the case of inter-source travel, where the drone, if it has not reached its full capacity, it will go to one source and then fetch the remaining packages from some other source. And the sources are connected to each other through the shortest possible path. The concept of the assignment algorithm is that we define a load for each of the sources. This load is calculated by multiplying the distance of that source to the number of time that source needs to be reached. So for example, if a source has 16 packages and a drone can fetch 4 packages at a time, it needs to be traversed 4 times to fetch all the packages from that source. So the load at that source will be 4 times its distance from the destination. So at every time step, we try to maintain a uniform balance of load. We try to balance the loads on all the sides of this graph, so that no edge has excessive load on it. So there's no lag at the end when all the drones have completed the task. I mean, the drones that have completed the task earlier don't have to wait for a long time for the last drone. So in this way, the overall task time is minimized. And the algorithm is implemented in MATLAB. We define a source class and a drone class. The properties of the source class are the packages, and the cost, which is its distance. The runs is the number of time it needs to be traversed to fetch all the packages, and remainder is if it has some remaining packages which are not multiple of 4. And so these properties are utilized for performing the assignment task. And similarly for drone, we have a position variable that indicates its position at a given time, and a cost incurred, which is like maintained in real time. As the drone keeps on traveling, it incurs more and more cost. And the packages is the number of packs it is holding at any given time. So the implementation is in MATLAB. We have an assign function. It takes 5 inputs, the number of sources, number of drones, and 3 arrays, that is the number travel time for each source, the packages at each source, and the time for inter-source travel. Based on these and the strategy we have discussed earlier, it outputs an assignment array having n columns, and in each column we have the source number for a drone corresponding to each time step. So in this way, we obtain which drone shall visit which source at which time step, and we certainly obtain the whole trajectory. Next, we verify our calculations by performing a simulation. So
this is the test case in which there are 13 packages in east, 5 in north, 7 in south, and 11 in west.
I think I'll need to share entire screen to show the linked video. Yes. So this is a video for the 2D simulation without inter-source travel. So the path of each drone is shown by different colors. One is red color, the other is green, and the third is blue. And we can see that they travel to different sources and fetch all the packages. I'm going to forward it because it will take more time then. So in this way, I mean, multiple iterations are performed until all the packages are fetched from all the sources. And here in this case, no inter-source travel is involved. So even if a drone has less than its full capacity, it won't go to another source. We are then comparing the results of both these strategies. This is without inter-source. Next, so the result for without inter-source is 84 seconds, the total time for this given test case. And next is with inter-source travel, and it takes 74 seconds.
74 seconds. So now we are.
Yes. So now we'll show the 3D visualization. In 3D, the trajectories I'll show the trajectory for with inter-source travel this time. So we can see both the cases.
So this was done in MATLAB Simulink 3D. So this is the case in which the drones travel with inter-source, means if some packages are left to be delivered after delivering at one agricultural site, instead of returning back to the warehouse, it will return to another inter-source. Another inter-source means another agricultural site to deliver those packages, left packages, and it will move back. So the advantage of it is that it will have more free space to travel, and so it will be a bit of more energy optimal path, and it was obtained as it is time optimal as well.
Yeah, we can see this case where the drone on the right, after visiting this source, it will go to the other source to fetch the remaining packages there. Yes. Okay. So We have less time, so we'll just move forward to the last aspect, the control.
So based on this, we have actually prepared a MATLAB simulating for the drone model, in which the input to this simulating model is roll, throttle, pitch, and yaw. So what we are controlling, we are actually wanted to control the drone motion, that is forward motion obtained by roll and throttle, left and right obtained by pitch and throttle. So we are actually connecting PIDs to roll and throttle to actually uh, having. So this is the PID performance tuning, in which actually the throttle is PID control is put into the throttle to check when there is no gust, that is half rho a v square. Wind is not there, so the throttle obtained was 38%. And in next slide, we are actually using PID auto tuning in MATLAB. Next, when gust is -8, half rho a v square is -8, that is downward force is -8. So it takes more time to settle, 7 to 8 seconds, and throttle 5% more, 43% throttle, as you can see in left side yellow. And this so it takes more time. Next. So this is the PID motion tuning which I discussed in the last slide. When you do PID auto tuning, in the right side figure you will see the yellow line is the throttle 50, and blue line is roll 20. So it actually, throttle is stationary at height, and roll means it's moving forward. Both combination of it is done by PID controller, but controlling more than 3 parameters is very difficult using PID controllers. Next. So our future aim is to actually develop a GUI application which will attach these small modules, graphical user interface, in which the user has to input the problem environment. The application will actually calculate the path to each of the source by any of the path planning algorithm. Then it will output those distance to the assignment. It will do assignment task, and final output will be visualization of swarm motion in 3D. So there will be various callback functions in MATLAB to integrate all these components in the project. Since it has control, it will generate control signals for real-time drone swarm control as well. Thank you.
So yeah, this is all verification of our modules, and now we want to connect them together into an application. Thank you very much for your interest.
Okay. Thank you for your nice presentation, both Abdul and Ronald. So I will request other participants, if you have any questions, you can quickly raise.
Hello.
Hello. Yes.
Yeah, am I audible?
Yes.
Yeah.
Yes.
Abdul and Robert, I'm having one question from you. How during the path transition of these drones, how you are making the coordination between the drones? Is are they in the coordination, or they are independently controlled?
They are independently moving, but we are avoiding collisions by building it into the assignment algorithm itself, so that no two drones. Yeah.
Okay. So they are not colliding. That means they must have some sensing capability, or what kind of, or you are using some algorithm based calculations?
Yes, so they are all following, yeah, algorithm based. They are all following the same generated paths, and we maintain a distance by building it into the algorithm. So they will not be at the same point at the same time.
Okay, so that means they are algorithmically driven, not they don't have any sensing capability.
I mean, sensor may be used as an added security, but this algorithm doesn't require sensors.
Okay. Thanks, Abdul. Thanks, Robert.
Thank you.
We have a question from Aniruddha. Aniruddha, please.
Yeah, so thank you, Ronald, and thank you, Abdul, for that presentation. I have just one single question. So, like, since the path is being generated, so what is the condition of optimality you have used for generating that path? Like, how can you say the path?
Actually, the PRM, we have used PRM inbuilt MATLAB functions. So any of the path planning, it won't be exact optimal path. It will generate a path. So we have used a multiple test case with increasing the sampling points and with actually start and goal point are fixed. What are the variables is node length and sampling points. So we have done various permutation combinations. By changing all this, we have obtained this PRM path, optimal, suboptimal. So we are actually taking optimal path.
So in a continuation of that, like if this algorithm needs to be implemented in real time, that permutation and combinations of the path would actually increase the time. So if there is some optimal,
so our since the PRM, since any of the path planning which give a path, so our main task is not the optimal path, but it should ensure a path. That is our primary task. So that is surely obtained by path planning.
Also, the task that is being done in real time is the assignment. The planning, path planning has to be done beforehand, and then the assignment of the task will be done in real time.
So I would request you like a kind of suggestion also, so that you can advance your algorithm in that. If you can consider some optimal criteria. So what happens like in dynamic environments is the kind of example you are seeing. So if you can assign some optimal criteria over the path that is being generated by your algorithm, if that can be done in real time, so that makes it more efficient. Okay, so if you're planning it like beforehand, and then like beforehand planning needs an idea of the environment. So in real time, the environment is unstructured. Okay, so you'll have multiple sensors that gives you an idea of it. So you can think in this direction. Okay.
Yes, sir.
Yes.
Thank you, sir. Thank you very much.
Hello, Abdul and Ronald. I have one question. One question definitely Aniruddha asked regarding that real time is that path planning. So my second question is that you have developed the controller. So you means your controller was highly nonlinear, and then you linearized it. How you approach the controller scheme in your
means I used PID controller to tune the controller parameters. It was non-linear as such, but MATLAB is this function or auto tuning. So I actually have to auto tune it. It will give me the reference and
okay. So means that your plant was non-linear, but you had not linearized it. You had directly used that auto tuner for that.
Yes.
That's an inbuilt MATLAB function.
MATLAB function.
Okay. Thank you.
Okay. Thank you once again, Abdul and Ronald.